arms in and they spin right on up like a top. Okay? Conservation of angular momentum with no angular impulse. What really goes on with an ice skater, though? Here's the concept. What goes on with an ice skater?
They're pushing off one of their feet as they're jumping up, so they'll pivot.
Well, once they get going, let's say they're already doing their thing. They're doing their spin, and they're up on the tip of one skate, or the front portion of one skate. And they bring their arms in. They do ramp up in their angular speed, don't they? We all know that. Is the impulse equal to 0 over time, numerous revolutions? There's a little bit of friction down there on the ice, and there's also, not much, that's why they're able to spin as long as they do. And then there's also air resistance against their body. Okay, so that they will slow down. Okay, and so there actually is some torque acting over time, which causes them then to slow down. Okay, so that's a nice little problem to illustrate that concept. Let's do another one of these. Any questions first before we move on? Okay. I think I covered the concept well enough. I tell you, there is one. I want to make a comment here, since some of you aren't caught up here on the homework yet. Let's see. This problem is in your homework. I'm just going to make some comments about it. So this 6 kilogram sphere over here on your left is in rotation. This thing is rotating counterclockwise initially, and then there's a little cup. There's a 4 kilogram cup over here on the right. And so as this thing's rotating, there is a 2 kilogram body here that is dropped from 6/10 of a meter. Dropped from 6/10 of a meter. So it's going to pick up some speed, and then what's going to happen as this rotating arm just becomes horizontal, that 2 kilogram cup, or 2 kilogram slug, is going to whack into this cup. The question is, what happens to the system after that slug is inside the cup? What's the angular velocity of the system immediately after the plug has wedged itself in that block? So this is just a square root of 2gh to find the velocity just before it hits. Okay? And that happens to be 3.43, just to make sure you get that part of the problem right in the homework. And then at that point, there's no torque applied to the system once that impact has occurred. Once that impact has occurred, there's no torque in the system, so we have a conservation of angular momentum condition. So you'll write the equation similar to what we just did in the last problem. And then your final result, you should get 0.1721 radians per second clockwise. So in other words, even though you have a fairly massive 6 kilogram and 4 kilogram parts here in counterclockwise rotation, there's enough momentum being carried by this 2 kilogram slug that it will cause the system to then kick around and go actually the other direction, clockwise. 0.1721 radians per second. Yeah, Ian?
Does the math work out that they hit the same place?
Excuse me?
I was just wondering if the math worked out that they... I mean, you can't calculate the time of that one. The one on the left's going to be level, and the one.
Yeah, this was given in the problem. They said when the arms become horizontal is right when that arrives there.
Right. But I was just saying.
And you can design it so that it would occur experimentally, and then see actually what happens off of that. Okay, so I wanted to give you a little hint on that homework problem. Here's another one. Actually, this is the kind of problem I remember from my college days where I made a mistake on an exam. Highly unusual. Okay.
Like that does on the story.
Yeah. Okay, so take a look at this problem, which is also in your homework, number 248. The question is asking, what's the angular velocity again, like the last question, shortly or immediately after impact? And then once you find that angular velocity immediately after impact, what's the angular deflection theta after this bullet has come and wedged itself into the lower mass? So this time we have this arm made up of two masses in clockwise rotation initially, and this bullet is coming in at 20 degrees from the horizontal and impacting this. So what's going to happen is the impact is going to cause it actually to kick back and go the other direction at 2.77 radians per second counterclockwise. And then once you have obtained that value in your work, then you will do a problem to figure out that the angle that it rises to is 52.1 degrees. 52.1 degrees. Now, I'll tell you the kind of mistake I made when I remember, you guys will remember things 30, 40 years from now when you're far along in your career from things that you did when you were in college as well. This arm in rotation with both those circular masses, it has angular momentum about O, doesn't it? Mm-hmm. Okay. So there's some angular momentum in the system. What about this bullet? It's got angular momentum as well. The mistake I made as a college student is I treated that as linear momentum, dealt with the impact type of thing on a problem similar to this, and then went into angular momentum after that. So just be aware that we're talking about this whole system carrying angular momentum about this axis O that's coming out of the paper, And the bullet's carrying angular momentum, R cross MV. R cross MV. Okay? So just heads up on that so you don't make the same kind of mistake I made years ago. Oh, before, initially. The system is made up of the two masses on the arm, on the rotating arm, and the bullet. The system, all three of those masses are carrying angular momentum about O. With respect to, about the axis through O. Okay. So that'll speed up your solution process a little bit. Okay. I think that's enough said on that topic. All right. Now, I was thinking of, let's see if I covered the problems I wanted to. No, I wanted to do another one. Here's an entry-level problem that might not be a bad idea to go through just to review a few things from your statics background. And you might, to get your feet on the ground on this very first page in this section on angular impulse momentum, it might not be a bad idea for you to work one of those other introductory problems. But here, at a certain instant, we have this mass that's in this three-dimensional axis system. And what they're asking us for is what the angular momentum that mass under the action of force F happens to be carrying. and its velocity, notice, is straight upward at that instant. So it's on an axis with coordinates A, B, C as shown. Okay, so distance A, B, and upward C, and here's the object, and this is our point O, our reference point. So what they're asking us to write, I believe, is the angular momentum carried by this mass, M, about point O, as shown. So if you just take this thing directly from the vector operation, there's its definition. Then we could write this as our position vector made up of the components A, B, C, and we're crossing that with our mass with a velocity that happens to be simply in the z direction. 0I plus 0j plus vk. Okay. That sets up, as we went over the other day, we can use a determinant I, j, k with our elements of position vector A, B, C on the middle row, and then the bottom row with a mass factored out in front, since there's a scalar factor on each of those terms, and then we have 0, 0, v. So the only non-zero terms are going to be the ones that don't come through these two elements. Yeah?
Oh, I'm right-hand ruling.
Oh, he's right-hand ruling. Oh, got another thing from my college days I need to throw at you. I may have mentioned this before. When you're sitting there, if you're right-handed doing an exam, don't use your left hand.
Yeah.
Anybody done that?
No, but I can see.
I did it in physics in college, okay, because I'm so excited. I'm sitting here doing this and getting things backwards, and sometimes that doesn't go over real well. Okay. Okay. Okay, and you wonder how I got through college. Okay. Here we have our I-directed terms involving that, and so if I just look at those, I know the only I-directed term is going to involve this M, and then I'm going to be left with a bunch of other terms. So here I have a BV, and nothing else with I, and then the J terms, that disappears. This one is non-zero, but it's going the negative direction, so it's minus AVJ. And then the K-directed term, this one zeroes out, and so does the other one. So there's your answer right there. Check out the units on the answer. Kilogram, meters per second. So we get kilogram meters squared per second, which are units of Newton meter seconds. Because a Newton is a kilogram meter per second squared. kilogram meter per second squared needs we have an extra meter sitting there, and we need an extra second up here to form a Newton meter seconds. If you don't remember that, what did I suggest the other day? Go to the other side of the concept and think about the units of the angular impulse. Newton meter seconds. Okay? Okay. So that's the first part. What was the other part of the question? Rate of change of the angular momentum? Rate of change of the angular momentum. Last class session I did this with you, and I'm going back over this because listening theory indicates you remember or hear about how much of what's said. About what percentage?
33%.
About a third, roughly a third of what gets said. Some people will hear and retain more than a third, and others will retain less or zero, okay? Particularly if you've got your head down on the desk sleeping or something, okay? Okay? So I say things typically several times. Sometimes I don't know that I'd said it before, but oftentimes it's because of that repetition is necessary to make it sink in. So this is, I went through this with you the other day. This is the definition of the angular momentum. And if we look for the time rate of change of that, we have to differentiate this thing. So if you ever forget it, just go ahead and do the work. Differentiating this is V. Leave this other one alone. You're dealing with a vector cross product. Plus, leave the r alone, crossed with m times the derivative of velocity is your acceleration. And v cross v we talked about is 0, because they're in the same direction. The sign of 0 is 0. And over here you have r cross f. So what they were asking for in part B of that question is what is the time rate of change of the angular momentum? Exactly this. So what we then need to do is to simply form the cross product given the prescribed force, which happened to have been in the y direction. Okay. So we have our A, B, C position vector, and we're crossing that with our y-directed force. The entire force is in the y direction. Okay. That again will set up as an IJK, a ABC, and this time a 0, F, 0. And so I see a term, non-zero term coming through here, picking up these two elements and wrapping around and picking up that K. So I'm picking up AFK. And I should get some other non-zero terms. Here's one coming this way. I have a CF come around and pick up this element, CF in the I direction, negative. And that should be it. Normally you write the I-directed terms first. So we'd write this as CFI plus, I'm sorry, a negative on that, CFI plus AFK for the first derivative or the time rate of change of that angular momentum. Try to remember that the time rate of change of the angular momentum is equal to the moment, the applied moment.
Do you have the net force?
Excuse me?
Is that the net force?
That's the total, that's the magnitude of the total force that they gave us in this problem. They only gave us one element, didn't they? Just y-directed. Total force was in the y direction. Okay. Come back for a second now and look at the geometry. Here's the particle moving at this instant. At this instant, it's moving straight upward. There's this applied force acting to it. So what's going to happen to the path of the particle? This is an unbalanced applied force.
In the y direction?
It's going to start coming out in the y direction, isn't it? Only in the y? It looks like the only acceleration's in the y, so, and the velocity was straight upward, had no x component going, did it? No x component or y component on the velocity. So I think it's just going to arc up this way. Now, go back to your statics background for a second. Notice that this point, the line of action of this force, is passing through the xz plane where? It's back up over here, isn't it? Isn't it back up here? Here's the line of action of that force. See it? And so look at the moment created by that force about O. Around the axis, the x-axis here, with my right hand, see it? It's negative on a lever arm of C times F, isn't it? C times F, and it's negative, going back in the negative x-axis direction, because the force is up here above. And that should be a negative C times lever arm, or times force F. And this is 90 degrees right here. It's a 90-degree angle. Something from statics, negative CFI. Right here, negative CFI. Okay, let's go back over there.